Hello everyone. So today we're going to start on 12.1 vector fields. Um, Chapter 12 is our beginning as serve as an introduction to a system of differential equation. So before we actually get to talk about vector field, which we're going to talk about a little bit about system of differential equation first. So in the last two chapters, 10 and 11, we learned how to solve a differential equation where the solution is a real value function of a single variable. So what we want to do now is try to talk about what happens if we have a system of differential equation. Okay, as I said, solving one single differential equation is not hard enough. So let's try to do a whole system of them. So when we're dealing with a system of differential equation, this is what we're going to do. We will generally use t to indicate our independent variable. And as a matter of fact, I'm not going to actually refer to it as an independent variable because when we're doing a system of differential equation, our solution actually is a vector value function. So our t actually work more like a parameter instead. So I'm going to say that it just becomes the variable with which we're going to take the derivative with respect to. So meaning the OR derivative would be something d something over dt. And on the other hand, we will use xyz as the space coordinates. So we therefore basically defining a position in space using the t variable, which is like time variables. Only, of course, up to R3, just like how we normally would do it. In dimension higher than R3, we will resort to using subscript notation. So therefore, what does that mean? Well, meaning basically the following. In R2, our vector x would be xy. In R3, our vector x would be xyz. And then in R4, our vector x would then become x1, x2, x3, x4. And then this continue in Rn. We'll say that vector x would equal to x1, x2, to xn. And then in all this scenario, they are all defined as functions of t, where t become a parameter, but in here you can think of it as a time variable, and then therefore in R2 and the vector x is defined as a position function. So you are basically using this to describe kind of like a movement of an object within whatever space we're working with. So how do we actually deal with this system? So what I want to do is basically talk about how we generally deal with a differential equation. A quick review on that first, because the idea is that we're going to try to basically deal with a system the same way we would deal with a single equation, by simply just take a system and kind of rewrite it into a vector equation. And I can deal with the vector equation just like I would normally do with a single differential equation. So that would be the goal that we're going to try work toward. So let's see if we can do this. Okay, so we call a first order differential equation can be written this way. So let's say we have a first order differential equation of the form of dx over dt equal to some function f of tx. Now, okay, that might look unfamiliar because typically in BC calculus, maybe I'll write it this way, in BC calculus, you will see it as this instead. But of course, the problem here is that I don't want to use x and y and dy over dx because, as I already established, we want to use t as our independent variable, the parameter. So therefore, I basically change the x to t and the y to x. That's all that is. Okay, and when you list the function cap f, you will list the independent variable, which in this case t, first, and then the dependent variable, which is x. So we call that you can have a function, we call a first order differential equation of the form dx over dt equal to f of tx. We'll have a real value function of a single variable. As the solution. And of course, this solution will be x of t. So a very simple example we're following. Let's say, for example, let's say with this equation, let's say if capital F of tx is equal to x plus t, then the differential equation that we have would look something like this. We'll turn to this, dx over dt equal to x plus t. And then if I simply rewrite dx over dt at x prime and move the x over, I would have my equation in what we call normalized form. And I can also rewrite it into a differential operator form. And we can now see that this is a first order linear differential equation, but non-homogeneous. Okay? Which is a first order linear non-homogeneous differential equation. And you learn how to solve this differential equation from chapter 10 and chapter 11 already. So the solution to this one, you can definitely verify that. But the solution to this equation, using some of the technique that you have learned from chapter 10 or chapter 11, should be this. Okay? I'm not going to go far to solve this. You should be able to figure this out on your own. And if not, you should definitely review what you learned in chapter 10 and 11. Because this is a very basic differential equation. And we spent 2 chapters on learning how to solve it. So you definitely need to know how to do that on your own. So now comes the question, what if we have multiple of these? So the problem here is that if we have multiple of these, then therefore we must imply that we have multiple dependent variable. Because in order for you to have multiple differential equation, then they must be relating to different derivatives. So similarly, let's say we have a pair of equations. In this form, let's say dx over dt equal to some function t xy, and then we have a second derivative dy over dt, which equal a different function of t xy. Then this pair of equation is often referred to as a system of dimension 2. Because they have two derivatives. That's why I call a system of dimension 2. And also understand that these two derivatives are related to two dependent variables, which are x and y, with the independent variable t. And in this case, this system has a solution, consists of a pair of function, one defined for x and one defined for y, a pair of function x of t and y of t over some interval from a to b. So that pair of function over a to b would now form actually kind of a curve. The reason why that is the case, because remember, this is more like parametric representation. So therefore, if I think of it this way, as t increases, or you can think of as t changes, but in this case, I'm going to say, let's say as t increases from a to b, the coordinate x of t, y of t would actually trace out a parametric curve. Oops. On the xy plane. So essentially, the solution to a system of dimension 2 would basically be a function that is mapped from R1 to R2. And this curve has a name. Such a curve is called the trajectory of the system. And therefore indicate that the solution to a system of dimension 2 is basically a curve in R2. And so the important part is that I can actually now interpret the solution to this system as a vector value function of t. So we can interpret the solution to a system of dimension 2 is a vector value function of t. T. Therefore indicate that our function f that map from R to R2 and f is in the form of f of t is equal to x of t, y of t. And the image, meaning the graph, of f of t is basically the trajectory of the system. Now, of course, here the important part is to understand that the 2 here and the 2 here are actually corresponding to each other. Therefore, indicate that when you have a dimension 3 system, a system of dimension 3, you actually be looking for a solution that map from R1 to R3, and then so on and so forth. Now, of course, we're not going to try to solve a really big system, because solving a system of differential equations is actually very difficult to do. So we're going to try to keep our system to be small, maybe dimension 2, maybe dimension 3 at most, but we won't be dealing with like massive dimension like 12 or something like that, because we just won't be able to do such a problem. Okay, remember this course still, no matter how difficult you think this class is, it's still just an introductory to differential equation. So give you a fair example. Oops. Example. Let's say we're going to try to solve this system. So let's try to solve this system. So now this system is actually very easy to do. The reason why it's very easy to do, because this system involves two unknown functions of t, x and y. But the nice thing about it is that the derivative of x is only relating to x, and the derivative of y only relating to y. Obviously, normal system, most likely the derivative of x would relate to x, y, and t, and the derivative of y will relate to x, y, and t also. And that's when those three variables mangle together, mix together within the derivative. That's what makes it hard to solve. So this is actually quite easy to do because of the fact that the two derivatives are independent of each other. So note, dx over dt is independent of y, and dy over dt is also independent of x. Therefore, we can simply solve this system as two separate differential equations. And both of these differential equations are extremely easy to do. As a matter of fact, it should take you no more than I would say 20-30 seconds to solve both of these. Okay, so if you look at this and you're not sure what to do, you really need to study some more on chapter 10 and chapter 11, because you can't solve a system of differential equation if you don't know how to solve a single differential equation to begin with. Okay, I would suggest that you pause the video and just go ahead and solve this system, solve these two differential equation, and then come up with the answers. Okay. All right, so hopefully you give it a try. Once again, let's go and do this. So dx over dt is equal to x, imply that x prime equal to x. That means that x prime minus x is equal to 0. That means d minus 1 of x is equal to 0. Indicate that the characteristic root is 1. So therefore, my solution must be this. And see, we're going to have two separate equations. I'm going to call this is C1. dy over dt equal to 2y. So therefore, basically telling me that y prime is equal to 2y. Therefore, meaning that y prime minus 2y equal to 0. That means it's d minus 2 of y equal to 0. Indicate the characteristic root is 2. So therefore, y must equal to c2e to 2t. There you go. As I say, take probably like 30 seconds to do. So therefore, now we know what the solution is. So the solution to this system is basically a function f of t equal to c1 e to t, c2 e to 2t. And so that is basically what we call the trajectory. Now, of course, because you have two unknown constant, how about if we have some kind of initial condition? If we are given the initial condition let's say x of 0 equal to 1 and y of 0 equal to 2, then we can find a specific solution. So what is this specific solution? Well, if x of 0 equal to 1, that indicate that 1 is equal to c1 e to 0. So therefore tell me that c1 equal to 1. And y of 0 equal to 2 would tell me that 2 is equal to c2 e to the 2 times 0, which is 0, 0. So therefore indicate that c2 would equal to 2. And so therefore that tell me that x equal to e to the t, and y is equal to 2 e to 2t. So therefore now with this initial condition, we can now say that the trajectory of the system is f of t equal to e to t 2 e to 2t. And the interesting thing is, if you were to graph this equation will trace out this function will trace out half of the parabola, y equal to 2x squared, with x and y both greater than 0. Yep, greater than 0. It can't be equal to 0 as a matter of fact. And if you're thinking like, how do I know y equal to 2x squared? If you simply plug in e to the t into x, you found that y, in this formula, you found that y would be 2e to 2t. So now comes the big question. So that example right here kind of illustrates the solution to a system of two differential equations, which actually form a function that went from R1 to R2, which forms some kind of curve on the xy plane. And of course, now before we actually get into harder differential equation, let's talk about what we just did. Since the solution is a vector, because it's function that went from R1 to R2, maybe we can rewrite this system into a vector notation to try to condense some of this stuff. So how do I do that? Well, how about simply we do the following. Let's say we let vector x to be xy. And let's say we let d vector x over dt be equal to dx over dt and dy over dt. So in this case, if our capital F of xy, which is basically capital vector F of vector x, is equal to x to y, then the system dx over dt equal to x, dy over dt equal to 2y can now turn into this vector equation. Oops. Now in this case, since our function capital F is independent of t, therefore there's no t involved. Now however, if it is dependent on t, then we can write into this general form, which is basically what we want to do. If capital F vector F of if capital vector F is dependent on t also, such as this system, Then, in vector form, this system will actually turn into this. The system will be this instead, will be d vector x over dt equal to vector f of t vector x with capital vector f of t vector x equal to x plus y minus plus t and x minus y minus t. And in this case, when you list the variable, you will list t first because that's the independent variable, and then you list the vector x or the variable x and y in order. So therefore, this could also be written this way, if you want. All right, the last thing I want to show you would be the following. What would a system of dimension n look like? So in general, a first order, we indicate this system is a first order system, and yes, you guessed right, there are second order, third order, high order system, but lucky for us, we will most likely only be doing first order system, and maybe some example in second order system. A first order system of dimension n in what we refer to as normal form will be a system in the form of where you just basically have a whole bunch of collection of differential equation dx1 over dt, which equal to f1 of t x1 x2 dot 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 to xn, and then you have dx2 over dt, which is f2 t x1 x2 dot 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 to xn, and then this pattern continue to dxn over dt, which is equal to capital Fn of t x1 x2 dot 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 to xn. And of course in R2 we'll just have dx over dt and dy over dt, and we'll have f1 of txy and f2 of txy. And then if is in R3, then we'll have dx dt, dy dt, and dz dt. And then we'll have f1 txyz, f2 txyz, and f3 txyz. Now, of course, you can probably guess that that's a lot of writing in a big system of dimension n. So, of course, what we're going to do is using vector notation with the following: vector x equal to x1, x2 dot 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 to xn. D vector x over dt would equal to basically dx1 over dt, dx2 over dt, dot 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 to dot 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 to dxn over dt. And finally, vector f of t vector x would just be equal to f1 of t comma vector x, f2 of t comma vector x, dot 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 to fn of t comma vector x. Then this entire system would just come down to one very simple equation. So then this system can be rewritten into a much more compact form. Oops. which is a lot easier to write than a whole bunch of equation. Now, one last thing I want to mention, and that would be it. So if I have a system like this, then important to understand is that in this scenario right here, when written this way, we can interpret d vector x over dt to be the velocity vector, or the standard tangent vector to the trajectory of the system. So it gives a nice, simple geometrical interpretation of what our system of differential equation actually mean. It's actually meaning that in this case, solving a system of differential equation is basically mean that we're given the standard tangent vector, or more importantly, the velocity vector. And now we try to simply find the position vector. So it gives a very nice geometrical interpretation of what we actually try to do. Unfortunately, that's all the time I got for today, so we're going to continue some more in our next video. All right, talk to you guys then. Bye-bye.